In other math classes, you accept that theorems are true. For example, the Pythagorean theorem, you would just assume that a squared plus b squared equals c squared in the sides of a right triangle. And for the proof that we're going to be doing today, we would assume that the monotonic convergence theorem is true, and then we would go ahead and use that theorem to conduct further analysis and use it in our calculations. So this theorem says that if a sequence is increasing and bounding, then it converges to the supremum of that sequence. For that, we would use that definition to then further solve a problem, whether in applied mathematics or just a straight calculus or algebra problem. But in proof writing, we want to show that these theorems or propositions or statements are true. You show that through logical deductions and definitions. For example, if you were to say that there are an infinite number of primes, this is just a simple proposition, you would have to say, demonstrate that this is true, or prove. And to do this, we would assume that there are a finite number of primes, or that the number of primes is limited, which is assuming the opposite of what we're trying to prove. This is called a proof of contradiction. To do this, we find a way to show that there's a last prime number. Once we show that this does not exist, then it follows that there's an infinite number of primes and our statement is true or has been proven. This is called a proof by contradiction. Today we're going to be doing a direct proof. One thing that we use to begin our proofs, because we're supposed to write them in a logical manner, is we use a proof guide. There are several steps to the proof guide. The one we use are 5. The first step is to write the statement in an if-then format. This is called a conditional statement. The if part is what you know, and the then part is what you're trying to prove. For our problem today, we were trying to show that if z sub n, the sequence z sub n, is equal to the infinums of a sub k for k is greater than n for all n that exists as natural numbers, where a sub n is a sequence and bounded of real numbers, then the sequence z sub n converges. This simply means that z sub n is a sequence consisting of the infinums of the sequences created by a sub k for k is greater than n. First, we need to write down what we know. This means writing down what's in between your if and your then statement. This is important because it shows what you already know and what you can assume, so you do not need to prove it. You actually use it to prove the then part. So we know that z sub n is a sequence consisting of the infinums of the sequence a sub n for a sub k as k is greater than n for all n as natural numbers, where a sub n is a bounded sequence of real numbers. From this, we will go on to expand it, but first, step 3 is to write down what we have to show. So this is what comes after the then in our conditional statement. What we have to show is that z sub n converges. This seems simple, but as you can see, it's going to get more complicated. So our step 4 is to expand what we know through definitions and formulas and expressions. Basically, we're taking what comes down in our if statement, or what we know, and we're expanding it so that we can get more tools to use to prove our statement. So we start with definitions. The definition of a bounded sequence is a sequence that is bounded if there exists a number m greater than 0, such that the absolute value of x sub n is less than m for every natural number n. This means it has to be bounded on both sides. The definition of inf. If we let a sub n be a non-empty set of real numbers bounded below, then the inf of a sub n for every epsilon greater than 0, there exists an element y in a sub n such that I plus epsilon is less than y. So now we come to other things we want to expand for. The limit of z sub n given in the problem is shown to be the limit inferior, known as the lim inf of a sub n. This basically means that the limit of z sub n is equal to the limit of the infs of a sub n, which is what it says in our up here for the a sub k. Now we know that z sub n is a sequence consisting of the infinums of sequences a sub k. The inf of a sub n is the greatest lower bound of the sequence. This means that it is the lowest number in the sequence. For example, we'll try to show what this means. So for our a sub n, this is just an example. It could be really any a sub n here. We'll assume that a sub n, beginning at n is equal 1, going to positive infinity, n is equal to n squared. Now for this, we know z sub 1 is equal to the inf of a sub n for n is greater than 1, which is equal to the inf of a sub 2, a sub 3, a sub 4, and so on and so forth, which is equal to 4, 9, 16, 25, 36, 49, and so on. So the smallest number in that sequence then, or the greatest lower bound, would be 4. So z sub 1 would equal to 4. For z sub 2, it's the inf of a sub n for n is greater than 2, which would be a sub n, the inf of a sub 3, a sub 4, a sub 5, and so on and so forth, which is equal to the inf of 9, 16, 25, 36, and so on, which would equal to 9. Same thing for z sub 3 is the inf of a sub n for n is greater than 3, which we can now see to be 16 because we're just taking out the lowest number from the previous sequence. From this we can see that the sequence would continue until z sub n reaches where n is the upper bound of a sub n. We also know that z sub n is bounded because a sub n is bounded and z sub n is a subsequence of a sub n. These things will all be important to know when we go to make our proof later. To expand what we have to show, this is step 5. So we want to provide definitions and explanations for all the parts that we want to show in our show statement in number 3. So a definition of a convergent sequence. We say that a sub n for n equals 1 to infinity converges to a real number x if and only if for every real number epsilon greater than 0 there is an n existing as a natural number such that x sub n minus x is less than infinity for all n is greater than capital N. It's important to note that x here is the limit of the sequence, so this is what we assume it converges to. And we must prove that this statement is true to show that the sequence converges to x. For other definitions that we need to know for our proof today, we're going to need to know the monotonic convergence theorem. Now we're going to prove it within our proof, but here's just a simple definition. If a sequence a sub n, beginning at n equals 1, going to positive infinity, is monotonic and increasing, then bounded, then it is bounded by the sup of a sub n, and it converges to the sup of a sub n. For the definition of monotonic increasing, a sequence that is increasing, that is for a sub n, where a sub n is less than or equal to a sub n plus 1 for all n is greater than or equal to 1. So basically, the next term in the sequence is greater than or equal to the previous term, is what we're trying to say. Now that we've laid out all the definitions and all things we're trying to prove in our proof guide, we'll begin to look at our clean proof. So remember again what we're trying to prove, to look at the statement we were trying to prove. We want to show that z sub n converges when z sub n is this sequence of the infiniums of a sub n for k is greater than n. So we begin by assuming, you always begin by assuming your if statement, or what you know. So we will assume that a sub n for n equals 1 moving to positive infinity is a bounded sequence of real numbers. Now we let z sub n equal the infimum of a sub k for k is greater than n. This means that z sub n is a sequence consisting of the infiniums of the sequences a sub k, k is greater than n, for all of a sub n, and all n existing as natural numbers. We want to show that z sub n converges. So here we've just laid out our know and what we're trying to prove. We will do this by using the monotonic convergence theorem, which states that if a sequence z sub n is increasing and bounded, then it converges to the supremum of z sub n. First, we have to show that z sub n is monotonic increasing. A sequence is monotonic increasing for z sub n where z sub n plus 1 is greater than or equal to z sub n. By definition, the infimum of a sub k for k is greater than n plus 1 is greater than or equal to the infimum of a sub k for k is greater than n. Therefore, z sub n is monotonic increasing. We can say this by definition because we know if the infimum is the greatest lower bound, we can always say that it is equal to or greater than the infimum of the previous statement. Because for k sub n, that is always going to be the lowest infimum. The greatest infimum. And then you would either increase it or it would stay the same. It's never going to lower. if we are increasing. So now we know that z sub n is bounded because a sub n is bounded, and z sub n is a subsequence of a sub n. Thus, we have shown that z sub n is a monotonic increasing sequence. We want to show, according to the definition of convergence, that z sub n converges. That is, z sub n minus L is less than epsilon, where L is equal to the sup of z sub n, and epsilon is always greater than 0. These are two things we'll assume. Since z sub n is bounded, it has a lowest upper bound, where that is the sup of z sub n, for n is a natural number, and this will be known as L. We are going to show that z sub n converges to L. Since L is the lowest upper bound, L minus epsilon is not an upper bound because we are subtracting a number greater than 0. Therefore, there is some capital N existing as a natural number such that L minus epsilon is less than z sub capital N, which is less than the supremum. This is for all little n is less than or equal to capital N. All this is saying is that if we subtract epsilon from our supremum, it is going to be less than some element of the sequence z sub little n, and this element is z sub capital N. Now we know that this is also going to be less than or equal to L, because we have L. We're subtracting a positive number from L. Therefore, we know that z sub capital N is less than z sub n because the sequence is increasing. So there's some z sub n greater than capital N, z sub capital N, because we're subtracting from the infimum, which is, from the supremum, which is part of the sequence z sub n. So from that, we have the supremum, L, minus epsilon is less than z sub n, which is some number in the sequence z sub little n, which is less than z sub little n, because that includes the entire sequence, including the supremum, which is less than or equal to capital L, which is the supremum. And we know this because we are subtracting from the supremum, and the supremum is the greatest upper bound, which must be greater than every element, or greater than or equal to every element in z sub n, which we can assume is less than the supremum plus the epsilon, because epsilon is a positive number and we are adding it to the supremum. And then, if we conduct some algebra, we can get z sub m minus L is less than epsilon from the above statement. So we have z sub n, which is this little n here, and if we subtract this L over here, we know that this z sub n is less than L plus epsilon, and if we subtract that, we're able to get z sub n minus capital L, which is the supremum, is less than epsilon. And since we know z sub n is a natural number, they're all natural numbers, and L is a natural number, then we know that we can add the absolute value signs. Hence, by the definition of a convergent sequence, which we know from the previous page, z sub n converges to L, the supremum. And this definition is found here, where z sub n minus L, which is either the limit or what we are attempting to prove it converges to, is less than epsilon, for epsilon is greater than 0. And now we have shown that z sub n converges to L, the supremum, and ultimately that z sub n converges. So the question asks then, is there a proof, or is there a sequence z sub n where it does not converge to the inf of a sub n? Per the proof, the sequence z sub n does not converge to the inf of a sub n, it converges to the sup of z sub n. The sup of z sub n is the lowest upper bound of all the infinims of a sub n for a sub k, for k is greater than n. For the sequence a sub n is equal to n squared, we know that the inf of a sub n increases as a sub n increases for n. Now, for z sub n is equal to the inf of a sub k for k is greater than n, this always increases since the lowest term is always cut out.